We ended last time with that question, which was about the basic idea of what we're doing, representing, we're taking the ball spring model of a solid and abstracting it a little bit, so we're thinking of one atom, which is one mass connected to 6 springs, if you like, as representing being represented by 3 independent oscillators. So the 300 oscillators is going to be a model for 100 atoms. And when we talk about arranging quanta of energy in a system of 300 oscillators, what we're talking about, so if we have 100 quanta, one quantum is, of course, that amount of energy that you need to go from one energy level to the next energy level for one of these quantum oscillator devices, one atom connected to a chemical bond. And we calculated that amount of energy way back in Chapter 8. That was h bar times the square root of the interatomic spring stiffness over the mass of an atom. And we refined it a little last time, saying that we really expected the effective spring stiffness to be a little bit different, from 4 times as much as what we had derived from Young's modulus. But the basic chain is that we started from hanging weights on the end of wires, and from Young's modulus we were actually able to get the stiffness of the interatomic bond modeled as a spring. And we could use that to get the speed of sound in a solid, but now we're actually looking at it to find out things about the internal energy. And today we're going to take the final step and actually use this very simple model, just balls connected to springs, to actually predict the specific heat capacity of a material from the principles that we've got. So that's a fair step. We made an assumption along the way, and so we have assumed something about what's going on at the microscopic level here. And what this is, it's a little bit different than the representations we've been using, but the idea is that we've got a particle that's got 100 oscillators in it, which is, 33.3 atoms. And so we're representing each oscillator just by one box in this matrix. And we have 25 quanta of energy to distribute throughout it. And the question is, which of these arrangements of energy is the most probable? Well, so 1 and 5. So what is the term we'd use to describe? Oh, these are C and D. You can't see them. Sorry, they're cut off. What is the term we'd use to describe diagram A? It is a what? It's a microstate, isn't it? We have this 25 quanta of energy, and we've arranged them one way among those 100 oscillators, so that's a microstate. And B is another microstate, right? And this is another microstate, and that's another microstate. So those are all microstates. What's the macrostate? What is that? No. A macrostate just says there's 25 quantum energy. The total amount of, here's an object, here's the energy it's got. It's all, since we only have one object, it's all in that object. That's a macrostate. So all of these are microstates corresponding to the same macrostate, right? Now, what did we assume in order to do all this calculation? What did we assume about different microstates? They're all equally probable. So all microstates corresponding to a given macrostate, which is our 25 quanta of energy, they're all equally probable. Now, this isn't all the microstates, is it? There's a lot, right? Yeah. So we just picked 4. So these are all equally probable. Now, there may be a lot more microstates that correspond to small amounts of energy and more oscillators. If you wrote down all the possible arrangements here, you'd see a lot that kind of look like those and not very many that look like that. In fact, there's only 100 different microstates that have 25 quanta of energy in one oscillator, right? And there's a lot that you can do that way. But each of these, we've sampled 4 out of an extremely large number of microstates, and each of these is in fact equally probable. And that's the fundamental assumption we're making that allowed us to figure out that entropy was directly related to the number of possible microstates for a given macrostate, the number of possible ways of arranging energy, to calculate entropy, and then to understand that temperature was related to the rate of change with entropy. As you started shoveling more quanta of energy into this system, there'd be more ways to arrange it, so the entropy would go up, and the rate at which entropy goes up as you add energy turns out to be the inverse of the temperature in Kelvin. So we can get an approximate Kelvin temperature by just dividing an energy change by an entropy change. And today we're going to take the next step and figure out how we can actually get specific heat capacity. But first we want to do a calculation and think about, we also talked about what we're calling the second law of thermodynamics, which says that if a system isn't in equilibrium and it's isolated from the rest of the world, the most probable thing that can happen is that the entropy of the system will increase. That when it gets to equilibrium, entropy will be at a maximum. So we have this relationship between temperature. So we have 1 over temperature is equal to the rate of change of entropy with energy. Now, we know something about this, that this isn't really a continuous function. Taking a derivative is a little difficult because energy keeps getting added in little pieces, so you can't figure out what's happening when you've added half a quantum. You just can't do that. So really, we can say that for our purposes, we can, if we can get a delta change in entropy over change in energy, we can actually calculate temperature, and we did one of those calculations last time. Now we could actually use this relation to calculate an entropy change in a system if we knew the amount of energy we'd put in, and if we managed to put energy into a system in such a way that its temperature didn't actually change or didn't change very much, then we could actually calculate its change in entropy. Well, there is actually a process like that. When a substance freezes or when a substance melts, so when a substance melts, so consider ice, you're putting energy into the ice, and it's going in as thermal energy, right? It's this internal energy, thermal energy. You're putting energy in, you put energy in, you put energy in. The ice warms up, warms up, warms up. And then it gets to the point where it's melting. And I don't know if you may have actually done this experiment in a chemistry class. So if you plot, you're measuring temperature versus time, and you're heating some ice. And so the ice was below 0 Celsius to start out with. So the temperature goes up and up and up and up and up, and then it starts to melt. And an interesting thing is that while it's melting, the temperature stays constant because you're not putting in energy to make the atoms in the lattice vibrate more anymore. What you're doing is actually breaking bonds between different water molecules. And so then when it's melted and it's a puddle, then it starts to go up again. But this is during the melting process, the temperature is actually constant. And it turns out that for water, to melt 1 gram of water requires about 335 joules of energy input. So we could actually do two things. We could calculate the entropy change of a gram of water when we melt it. We could calculate the entropy change of a gram of water when we freeze it. And we could also calculate the entropy change in the surroundings, just to see if it's true that the change in entropy of the system plus the change in entropy of the surroundings is never less than 0. It's always the entropy of the world, the universe, is always increased. Okay? So let's do that. And we can think about it this way, just to be very concrete. So what we'll do, we'll take a block of ice. It's 1 gram, and it's at 0 Celsius, which is 273 Kelvin. And it's in contact with some big block of room temperature metal, which is at 293 Kelvin, so it's warmer. That's where that energy is coming from to melt it. And so we can say, well, delta, looks like we can rearrange this equation to say that if we could calculate the change in the energy of the object divided by its temperature, that ought to give us the entropy change of the system. So let's look at this. So we have the change in entropy of the ice here. Well, we're putting in 335 joules to melt it. And the temperature of the ice is 273 Kelvin. And so that number is bigger than 1. That looks like it's about 1.23 joules per Kelvin. So the entropy of the ice, the entropy of the water increased when it went from ice to water, right? And there must be more ways to arrange that energy. What happened to the surroundings? We have change of entropy of the surroundings. Well, that was a negative 335 joules, because 335 joules flowed from the metal to the ice. But that occurred at 293 Kelvin. We had a big enough block of metal that its temperature just didn't change very much. It was a negligible temperature change. And so that comes out to negative 1.14 joules per Kelvin. So the entropy of the surroundings did decrease. but it seems to have decreased less than the entropy of the ice increased. So delta S of the system plus delta S of the surroundings is equal to that plus that. And it's a positive number, so it looks like it's 0.09 joules per Kelvin. So the entropy of the universe went up when we melted that ice. Okay, suppose we did it the other way and we were freezing ice, freezing water. So we're going to do it the other way. So we're going to take, here's a block of metal at 253 Kelvin, so minus 20 Celsius. And we're going to pour our little gram of water here at 273 Kelvin. So let's calculate the entropy change for the system and for the surroundings in this situation. So how do I calculate the entropy change for the water? What's that going to be equal to? How did we do it last time? So we use the change in energy of the system divided by the temperature, right? That works as long as the temperature is not changing. So what numbers do I put here? No, negative 335 joules. Because in order to freeze, it's melting backwards, isn't it? Yeah, so if it takes 335 joules per gram to melt it, it has to give up 335 joules per gram to freeze. If something freezes, it's losing internal energy, right? And divided by what? 273. So does the temperature of the water change when it's freezing? Yeah, we saw that curve, right? So it's actually when it melts or when it freezes during that process, it's actually constant. And so that's going to be a negative number. And it looks like negative 1.23 joules per Kelvin. That's not a big surprise. It was positive 1. What about the surroundings? What do you think? Is the entropy of the surroundings? It better be, huh? Yeah, we think so. So how do I calculate the entropy change of the surroundings? Okay, 335 joules flow from the ice to the surroundings. And the surroundings stays at about 253 Kelvin. So that comes out to a plus 1.32 joules per Kelvin. And so if we add it up, it looks like we're still going to get a positive number. And it comes out to plus 0.09. So it looks like the entropy of the universe increased when we melted the ice, and it increased when we froze the ice. And if we keep freezing and melting this gram of ice, the entropy of the universe keeps increasing and increasing and increasing, and there's no way to keep it from doing that. So it looks like the second law of thermodynamics, at least in this situation, seems to be obeyed. The entropy of system plus surroundings is never decreasing. Now, it's just one example, but it does usually work out that way.